continue, what we learned so far. Review. We start talking about series. We try to analyze series using different tests. Series, then tests for series. We're interested in having convergence series, so we introduce different types of tests to be able to analyze those series. Then we said that, hey, let us make it more interesting. Let us define some new series that we call power series. We talked about power series. We're interested in analyzing power series for their convergence. So we defined R using ratio test to analyze the radius of convergence, the interval of convergence. The radius of convergence. We denoted that by R. Remember that we used our ratio test to find R. Then we said that, hey, this R actually gives, for example, a boundary for X, if A is equal to 0, for X, and suppose this is your R, but it doesn't tell us anything about the boundary values. It says X is bounded between -1/3 and +1/3. What if I plug in X equals to -1/3? Is the series, the original series, convergent? Is it divergent? What if X is equal to +1/3? What we can tell about the original series? So in these two cases, we need to plug boundary values into the series and analyze its convergence. Very well. So we start talking about power series, and then we wanted to talk about Taylor series and special case Maclaurin series. Power series was defined as the sum Cn x minus a to power n starts from 0, goes to infinity, and we saw that by using the ratio test, we can find the interval of convergence. Interval of convergence. And R is our radius of convergence. By analyzing the boundary points, we either do not include any of these, we might include both of these, or just one of these boundary values. Well, we also said that, hey, for a function like f of x, if we have a function like f of x, and it has a series expansion like this, f of x equals to the sum Cn x minus a to the power n starts from 0 to infinity. There is a connection between these coefficients, these numbers, and the derivatives of this function. So Cn, all these coefficients, all these numbers can be written as the n derivative of function evaluated at a, center a, divided by n factorial. And remember that we have to include the interval of convergence as well. Okay, let's take a look at one example. Then we go over two theorems and we try to analyze the remainder of function. Let's take a look at one example. For our exponential function, we're going to write down the Taylor series at a equal to 0. We actually have a name for it. We call it Maclaurin series. Example, write Taylor series for e to the x at center a equal to 0. Let's write the note here. Taylor series for a is equal to 0 is called Maclaurin series. So Maclaurin series is a special case of the Taylor series. So when the question says, hey, write Taylor series for e to the x at a equal to 0, means that they are looking for the Maclaurin series. We know that f of x is equal to the sum Cn x minus a to power n starts from 0, goes to infinity, and the absolute value of x minus a, or the distance between x to a, x to the center, is less than r. In this case, our a is equal to 0, so e to the x is equal to the sum Cn x minus 0 to power n, or x to the n starts from 0, goes to infinity. Absolute value of x is less than r. And we define Cn. Guys, the definition is important. You always have to look at the definition. Cn is defined as the nth derivative of function evaluated at a. Our a is equal to 0 divided by n factorial. So e to the x is equal to c sub 0 x to 0, c sub 1 x to the first power, c sub 2 x squared, c sub 3 x cubed, plus the rest of the terms. We need to evaluate each of these numbers, coefficients. So these are just numbers. This is a number, this is a number, this is a number, this is a number, or these are coefficients. So to find c sub 0 is equal to the 0th derivative of function at 0 over 0 factorial. The 0th derivative is equal to the function itself. So this is actually e to the x. Where do we evaluate x? When x is equal to 0. Divided by n factorial, 0 factorial, or just 1. You get e to 0 divided by 1, which is equal to 1. So e to the x is equal to 1 times x to the power 0 plus c sub 1 is the first derivative. N is equal to 1. The first derivative of the function when when the value of the function is equal to 0 divided by 1 factorial. The first derivative of e to the x is e to the x. So e to the x evaluated at 0 divided by 1 factorial, which is 1. Again, we get e to 0 divided by 1, which is equal to 1. 1 times x to the first power plus c sub 2. We continue this process. C sub 2 is the second derivative of function at 0 divided by 2 factorial. The second derivative of e to the x is e to the x. So we're going to get e to the x evaluated at 0 divided by 2 factorial. So you get e to 0 divided by 2, or it is a half. A half x squared plus, if you do the calculation, continue that, you get 1 over 6 x cubed plus the rest of the terms. Well, this is expanded form. This is expanded form. We want to write this in compact form. We need to find the pattern here. X to power 0, x to power 1, x to power 2, x to the third power, x to the fourth power. So e to the x can be written in compact form, sum x to powers. X to powers is super easy to recognize. X to power n, and n starts from 0 to infinity. What do we do with these coefficients? The first coefficient is 1. Take a look at what you had before. It was 1 divided by, it is 1 divided by 0 factorial. So this is 1 divided by 0 factorial, which was 1. So you have 1 divided by 0 factorial. The second coefficient is e to 0 divided by 1 factorial, or 1 over 1 factorial. So this 1 was actually 1 over 1 factorial. The third coefficient is a half. It was 1 divided by 2 factorial. 1 divided by 2 factorial. 1 over 6 is nothing but 1 over 3 factorial. Take a look at the denominator, n factorial. So it means that 0 factorial, 1 factorial, 2 factorial, 3 factorial, and the rest of them are located on the denominator, n factorial. So this is our compact form. So what is the conclusion? The conclusion is that this is the Maclaurin series of function e to the x, or you can say that the Taylor series of e to the x at a equal to 0. This is the Maclaurin, or Taylor at a equal to 0 series of e to the x. There you go. A theorem for you.